So today we're going to start Learning Target 3 and then we will finish it tomorrow. Learning Target 3 is all about making and interpreting graphs of exponential functions. So first of all, for part 1, we're going to remember that a graph is really just a representation of all of the x and y ordered pairs that would make the function true. So that are like a solution to the function. So if this is our graph that we're going to think about right now, and I filled mine in a little bit more because it's really hard to see just because it printed badly. We're going to think about these 4 points and ask ourselves, based on this graph, are each of these points a solution to this function? Which means basically, does each of these x, y ordered pairs lie on the graph of the function? So the first one is 1, 2, part of the solution set of this function, and 1, and then this is 1 going across there. 1, 2. Yes, it is because it's on the graph. Is 2, 4. So 1, 2, 1, 2, 3, 4. Yes, it is because it's on the graph. 1, 6. 1, 2, 3, 4, 5, 6. Like right there. No, it's not because it's not on the graph. It's not on the line here, or not line because it's not straight. But you know, the graph of the function, it's not on that. And then 3, 8, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. That is way up there. Yes. And we can also use graphs to write functions to try to get the rest of the solutions if we want them. The value of a, remember, is just the y-intercept. So a equals 1. The value of b is the pattern of how it's changing. So if we were to turn these ordered pairs into a table, we take 0, 1, 1, 2, 2, 4. We could even go 3, 8. If we were to turn those into a table, we can see that it is multiplying by 2, which means our b value is 2. And once you have a and b, you can use those to write the function, because remember, exponential functions follow this pattern, this template, a times b to the x power. So if a is 1 and b is 2, it'll be 1 times 2 to the x power. And that's how you write an exponential function from a graph, and that's how you can use the graph to determine which ordered pairs are solutions to the function and which are not. The second part is looking at how we can use graphs to help solve problems. So consider that this is a graph of a system of 2 exponential functions. We've looked at graphs of linear systems with 2 lines. But you can really have a system of any type of function. A system is just 2 graphs on the same grid, or 2 equations bundled together, or more than 2. So here's a system of exponential equations. We know, so one of them is 1 times 2 to the x power. That's this one. And I know that because a is 1 and this one has a y-intercept of 1. The other one is 4 times 1.2 to the x power. And I know that that's this one because a is 4 and this one has a y-intercept of 4. So first of all, what is the solution to this system? Well, we remember from Learning Target 7 in the last unit that the solution happens when the 2 graphs intersect. So for example, this graph represents all the solutions, all the ordered pairs that are solutions to 1 times 2 to the x power. This graph represents all the ordered pairs that are solutions to this equation. The place where they intersect is the one place that is a solution to both equations at the same time. So that is this ordered pair right here. So the solution is 2.714, 6.561. So that ordered pair, that x and y value, is the only x and y value that will make both this equation true and that equation true. We're looking at intervals. For what interval is f of x equals 1 times 2 to the x greater? So we're looking at this function right here, and this function starts to be bigger than the other function at this point right here. That's where they cross, and then suddenly this function is on top. It's higher up on the graph. Okay, so that means, and we always do intervals based along the x-axis. So all the x's that are greater than this value when they cross. All the x's, So here's going across to all the x's. When we get to that point right there, everything greater than that, this function is higher up on the graph. It crosses and it's higher over here. The other function is higher up on our graph. It's greater, has greater, bigger y values when it's before that. So all the x's that are less than the x value of our crossing point. Now imagine that these two graphs represent the money made in two different investment accounts. Which account would have more money if the money is left in it for 2 years? So here's 2. Which equation is going to have the greater value there at 2? And it would be the one with a y-intercept of 4. This equation is higher at the value when x is 2. So that function represents the account with more money in it at 2 years. If the money is left in for 5 years, now we're out here at 5 when x is 5. And if you follow it up, this equation would be the greater one, right? It would be greater way up there. So this one would have a value of 10, but this equation would have a value of a lot. I don't know what that is exactly, maybe like 30, I don't know. So that one is going to have a higher value, and that is the line that has a y-intercept down here at 1. So it's this function, whoops, equals 1 times 2 to the x power. So that's how you can use equations, and you can even have systems of equations that have different types of functions. For example, you could have one linear and one exponential, or a quadratic and an exponential, which we haven't talked about quadratics yet, but we will. So you can mix and match different types of equations in a system, and that's how you can use systems, especially systems of exponential functions here, to solve systems of equations. Tomorrow we'll start looking at graphing them and what that looks like. So enjoy.